let me recall a definition of lattice polytopes. So we have a real vector space, Rn, and we fix a finite number of points in this Rn. And the convex hull of them, this is a polytope. Well, what do I mean by the convex hull? Of course, I just mean a combination of those points when lambda i's are non-negative and they sum up to 1. That's a polytope. And we say that this is a lattice polytope if P equals a convex hull of Q1 up to Q whatever, but now we require the Qi's to have integer coordinates. So I just wanted to stress one thing. This presentation as a convex hull, it seems not unique. Yes, if I have a polytope, it is a convex hull of 20 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, 20. It is a convex hull of those points. But there is a minimal set such that this is a convex hull of. In this case, what's the cardinality of this set? 4. Yes, we have 4 distinguished points. And one can say that this is a subset minimal with respect to inclusion among the sets such that P is the convex hull of those points. And in such a case, these points are called vertices. Yes? So in particular, we will say that a lattice, that a polytope is a lattice polytope if it has vertices with integer coordinates. So that was just a reminder what is a polytope. And this we have already seen in the lecture about toric varieties. And now we pass to matroids. I assume most of you don't know what is a matroid. So the name suggests that it has something to do with matrices. But this connection will be only seen later. Right now, we will abstractly define a matroid. For that, we need to know that a matroid is a structure in mathematics that abstracts the notion of independence. So if you have been studying algebra, you know from linear algebra that someone can say that certain points are linearly independent. And if you've been studying like other fields in algebra, like field extension, you know that you can say that elements are algebraically independent. You could also say, in some sense, if you are doing combinatorics, that the edges of a graph are independent if they don't contain a cycle. And all these notions are somehow intuitive. We intuitively can call subsets independent. I mean, there is a formal definition, but why do we call them independent? And as we will see, all this structure, they are special examples of matroids. So what's our aim? Our aim is to first fix a finite set, E, and we would like to distinguish certain subsets of this set that we will call independent sets. So a matroid will be a family of subsets. By this, I mean all subsets of E, including the empty set and E itself. And a matroid will be some of those subsets. And the elements of I will be called independent sets. Before we will go further, let me make a general mathematical remark. So we know vector spaces and we know groups. And we know their formal definitions, but behind every concept, like a group or a vector space, there is some intuition, like a vector space should generalize the concept of space that is around us. And whatever is a vector space, we first say that it's a set with certain additional properties. Also the group, yes, we start with a set, but then there is also an action, an operation, and it needs to satisfy certain axioms. And in the same way, we will proceed with matroids. It's a family of sets, but of course, we would like to require that they satisfy certain axioms. And let's try to guess these axioms. Some of them are really easy to guess. Well, can you give me an example of a set that no matter which structure you would consider, you would call that all elements of this set are independent? Just one element, that's a little too much. If this element, for example, would be 0 in a vector space, then you wouldn't say that it's linearly independent, even with itself. But you're very close.
Non-zero elements.
Well, but we don't have a concept of 0. E is just a finite set.
Well, something that is minimal.
Yes, 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 yes. Empty set. I mean, and whatever we distinguish the independent things, I mean, an empty set should consist of independent elements. I mean, there are no dependence relations for elements of the empty set. And that's the first axiom, that the empty set belongs to I. Okay. Now, what do we require from independent sets? Let's say we already have an independent set. What else do we, let's say I give you an independent set. Yes, so we know that some set A is an independent set. What can we conclude from this? Think about, for example, linearly independent points in a vector space. Can you cook up some other independent sets from this one set? Yeah, say I give you 3 linearly independent points. Can you give me some?
Every subset of independent.
Yes. That's a very good intuition. I mean, whatever is an independent set, if we want to make it reasonable, a subset of it should also be independent. So I should say A is an independent set, B is a subset of A, then B is in I. Okay. These are very important properties. What have we defined so far? This is a well-known object, mainly in topology. Forget about matroids. What is something that satisfies these two things? How is it called? Well, it's just a simplicial complex. We work like on a finite set, but it's close to filters, yes, and that's true. But it's a very basic object. It's just a simplicial complex. Yes, we say that something is a simplicial complex. Each time we have a simplex, then every subset of it is also a simplex. Okay? So clearly we are not yet at matroids. We need something more for independent sets. And what it turns out is amazing is that we just did one more axiom. So one of the mathematicians who obtained famous results on matroids, a young mathematician, is Jun Ha, and I remember his lecture about matroids, and he said that throughout the years he learned how much one should appreciate this last axiom. It seems just a short statement, but it has a very, very rich structure. Okay, so what will be this last axiom? Well, we need to really think about independent sets. So let's say we have 2 of them. And let's say that one has bigger cardinality. Can we conclude something from it? Again, think about vector spaces. Yes? So we have one set that is independent and large. So it spans a vector space of its own cardinality. And the second that is independent but is a little smaller.
Every independent set can be extended to a bigger independent set.
Very good, very good. That's precisely the axiom that we want. There exists an element B in B such that A union B is also independent. Okay. And what is amazing, this is the definition of a matroid. That's all. That's all. These three axioms. You have to be able to extend a small independent set by an element. And yes, this already, as we will see, gives a really, really rich structure. Perfect. So, because we were building our axioms on the intuition of linear independence, the first example of a matroid that we encounter is when E is a finite subset of a vector space. Any vector space over any field. Then we can construct a representable or realizable matroid. We call this a representable matroid. Where we construct a family which exactly consists of those subsets of A that are linearly independent. Okay, let's do an example, and you will construct a matroid. We have a two-dimensional vector space, which is this board. So if it is a vector space, it has a zero. I mean, every vector space has a zero. That's part of a definition. And now I will take my finite set. Yeah, so 3 dots. Let's label them. 1, 2, and 3. What is the matroid? It's a family of subsets. And I hope you can give me the subsets. What's there?
So the empty set.
The empty set, very good. 1. The set consisting of 1. The set consisting of 2. The set consisting of 3.
It can be the whole power set of this.
Sorry?
The power set.
The power set. So let's think about it. So maybe my picture isn't very good, but I was trying to.
2 is a multiple.
Sorry?
2 is a multiple of 1.
2 is a multiple of 1. And further, we are in a two-dimensional vector space. So having 3 elements linearly independent is unlikely. Okay. So even if they were in a generic position, but they are not, so it's even worse. Okay, so what else? Can we find some more independent sets?
1, 3.
1, 3, very good. Okay, now someone else, someone who hasn't yet, gave an answer today. What are other independent sets? Yes? 2, 3. 2, 3. Sorry?
I think that's everything.
Yes, I also think that's everything. Yes, so 1, 2 is not there. Huh? Okay. Very good. So this is a matroid, and well, of course, you can check that it satisfies the axioms. Very nice. Now, I also mentioned graphic matroids. This explains why we usually in matroid theory denote E the finite set. This is known as the ground set of the matroid. Okay? Because E stands for edges.
Sorry? Every subset of this set is also a matroid.
Well, no.
Why?
If I take, for example, just a subset consisting of 1, 3, it's not a matroid because it doesn't contain an empty set.
Including empty set, I mean.
Well, if I take empty set and 1, 3, it's still not a matroid.
Sorry?
If I take empty set and 1, 3, it's still not a matroid. For example, it doesn't satisfy the second axiom. There are subsets of it that are matroids. For example, I can just look at 1, 2, those sets that contain just 1, 2. Yeah? We will come to a definition there. So there is a restriction of a matroid. We will talk about it in a second. But it's not true that any subset of this family is a matroid. Okay, so we have a graph, and not usual graph, not directed. We set E edges of G, and we define the independent sets to be those sets of edges that do not have a cycle. There's no cycle in A. Okay. In the notes, you will also find examples of algebraic matroids that I will not write right now on the board, but I also wanted to mention a very easy but important example of uniform matroids. Here we fix any finite set. And we also fix some integer that is at most the cardinality of E. And we define I to be those subsets that have cardinality at most k. That's another example of a matroid. Any questions? So it might be not obvious that these structures are matroids, and this is in fact one of the exercises for you that is left to check that these are in fact matroids. Okay? But are the definitions clear? Okay. Maybe I should have stressed this once more. So a matroid is a family of subsets that satisfies these three axioms. Yes, so each time I give you a family of subsets that satisfies these three axioms, it means I have specified a matroid. Okay.
Sorry for the question.
Yes?
Just follow that, but why is the first axiom even necessary if we have the second one?
That's a very good question. Why is the first axiom necessary if we have a second one? Yes?
Otherwise, the matroid could be empty.
Yes, we want to avoid the trivial situation where I is just the empty set and there are no subsets at all. So I could have replaced this by saying that I is not an empty set. So if it has an element, then definitely empty set has to be there by a second axiom, but this is just to avoid a trivial situation and to have something in our matroid. That's a very good question. Okay. If you work with simplicial complexes, if you want to tell me what's your favorite simplicial complex, how would you do it? Can anyone give me an example of a simplicial complex?
A graph. A complete graph.
A graph, that's an example, but it's not a very convenient way. I mean, one would have to go to a board to draw a graph. But let's say you have a simplicial complex on 4 vertices. How do you give it to me? Imagine, take any simplicial complex. What's your favorite simplicial complex? Like a complete simplex, yeah. Yes? So how would you tell me what it is? You just gave me one piece of information. What was this information? You didn't tell me all elements of your simplicial complex.
Every two vertex, and then you connect every three vertex and so on.
Yes, so you take all subsets, that's true, but you didn't tell me take all subsets. You told me take the pyramid, the simplex. So how do you usually, when you talk to each other, present a simplicial complex? You don't give all elements of this simplicial complex. What do you give?
Faces.
That's very close, but you don't give all faces. Yes, if you want to tell your friend, like, take a pyramid, you don't say take all 4 vertices, then take all 6 edges that connect them, then take all 4 triangles, and then take a pyramid. Yeah, you don't do that. You just say the simplicial complex is the pyramid. Yeah. So in general, how would you do this? How would you tell your friend about this simplicial complex that is like full inside? Say you want to send it by a computer, but you don't want to waste a lot of memory. Yes?
Take a maximal independent set.
Very good, very good. That's exactly what we do. We don't say, because there is this axiom that holds. This one. There is this axiom that holds. So we do not need to specify all elements of a simplicial complex. We just need to specify maximal ones. Yes? That's the way to specify a simplicial complex. For example, to specify this one, you would say that there is a simplex 1, 2, 3, 4, and 2, 5, 6, 7. And that specifies the simplicial complex. So here, I just have to give you these 2 sets. They specify the matroid. The others are just subsets of those 2 sets. Okay?
So we can think about dimension and say how many simplicial complexes in different dimensions are there.
Yes, as we will see, it's even better because this axiom will force us to have all maximal simplices of the same dimension, but this will come in a second. Right now, I want you to accept the fact that as a matroid is a simplicial complex, better than thinking about all of those subsets in a matroid, it's better to think just about maximal ones. Yes, is this convincing? Because this is what we do for a simplicial complex, so we should also do this for a matroid. So a definition, a basis of a matroid M is a maximal. So when I write maximal, I mean maximal with respect to inclusion, is a maximal element of I. Yes? And the set of bases, the set of all bases B determines M. Is it clear? Any questions about this? The maximal elements, they determine the whole structure because it's a simplicial complex. Okay? And note that this definition is very much inspired by linear algebra. The bases of this matroid, are exactly the basis of this vector space. Okay? So in this case, this notion of basis is this, as we know it from linear algebra. Perfect. So matroids are amazing because they allow an enormous system of equivalent definitions. Right now we have defined them through independent sets. But then we observe that maybe it's enough to look at the basis. So certainly it's not true that any set will be a set of bases of a matroid, but it turns out that it's very easy to say when so this B it also belongs to 2 to the e, and when such a family is a family of bases of some matroid. So a proposition B is a set of bases of some matroid if, well, there is always this axiom that I always forget. We don't want B to be the empty set. And it turns out that there is just one more axiom. If we have 2 elements in B, and if we take an element that belongs to B1 but not to B2, then, let's call this element B1, then there exists an element B2 in B2 such that if we subtract from B1 B1 and add B2, we get a basis. Okay, so the picture is like this. I have 2 bases. B1, okay, I should label them here. B1 and B2. I pick an element B1, and I can find an element B2 such that if I take these elements, this one, and I don't take this one, I still get a basis. And you should think about what it means in terms of linear algebra, and you should prove as an exercise that these axioms are equivalent to this axiom. So this is an equivalent definition of a matroid. Yeah? So if we want to check if this is a matroid, we have to pick 2 bases. Yes? We need to, so the picture is like this. We have 1, 3, we have 2, 3. Well, there are not many elements we can pick for B1. We have to pick a 1, and clearly, in this basis, we can forget 1 and add 2 and still get a basis. Okay? And a remark that is also easy to prove, every element in a basis, or let's say, let's take any 2 elements, they have the same cardinality. Okay, who can prove it already? That the bases have the same cardinality? So think about this axiom. Well, bases are maximal elements of independent sets. So if one of them had smaller cardinality than the other, we would be able to extend the smaller. But then it wouldn't be maximal if we were able to extend it. Yeah? Okay. I should say that we can like strictly extend it. Okay. But I think this was clear. We can extend it, not keep it. Okay, so all bases are of the same cardinality, and this cardinality is known as the rank of the matroid. The cardinality of a basis is the rank of a matroid. Let's check if we are on the same page. What's the rank of this matroid? Well, everyone should shout a number, and I hope it will be the same number. 2, yes. Very good. Okay, so now the time has come to show you the power of matroids. These axioms look very innocent. They look, for example, much simpler than the axioms of a group or of a vector space. I mean, basically there is for bases, there is just one axiom, and for independent sets, there is one meaningful axiom. And yet, it turns out that we can derive a lot of non-trivial properties. When you look at this basis axiom, you should complain. I mean, it looks very non-symmetric. I picked an element in B1, then I subtracted it from B1. What is this B2 doing there? It looks a little bit unsymmetric. So it's a theorem that from this seemingly weak axiom, you can derive more, strictly more. Well, not strictly, because the definition of a matroid remains the same, but at least when you look at it, it seems a strictly stronger statement. So let's take M a matroid. With base set with basis B. And we have the following two properties. The first one is that if we take any two bases, the assumptions are just like in there. And if we take any element of B1, but the conclusion is stronger. Not only there exists a B2 in B2 such that if we forget B1 and add B2, we get a basis, but also if from B2 we forget the element B2, and if we add B1, we get a basis. Yes? So we only assume this, but we can conclude more. Huh? Isn't it amazing? Let's check it for those bases. Well, if I pick one, we said that I have to choose two. Yes, to change this basis into this. But it sort of happens that this basis, when it loses 2 and gets a 1, it's also a basis. Yeah? And I challenge you to prove it. It's just one combinatorial statement, and then this is another easy combinatorial statement. How hard the proof can be. Okay, and now even more. If we take two bases, and if we take any subset of B1, then there exists a subset of B2 minus B1 such that we can subtract from B1A and add A prime, and we get a basis, and we can subtract from B2A prime and add A, and we get a basis. So not only can we simultaneously exchange two elements, we can simultaneously exchange any subsets. Yeah? And that's an even greater challenge for you to prove this. But, well, this is really challenging. I mean, it's a non-obvious statement, highly non-obvious. So if you are able to prove it by your own, don't do other exercises about matroids. That's enough. So I hope I at least give you an intuition that matroids can be really useful, because say you have a structure that you feel that it should consist of independent sets. You just have to check such one property, and you get a highly non-trivial conclusion that also a much stronger property holds, and you get it for free. I mean, even for linear algebra, proving both of those statements can be a challenge. Okay. And I should say, so one is called a symmetric basis exchange. And two is called a multiple symmetric basis exchange. Yes?
And so is there some key idea that one has to have, or is it just difficult formalism that is challenging? I mean,
that's a good question. I mean, so the proof is entirely combinatorial. You don't have to know some theorems, but it's a highly non-trivial combinatorics that usually refers to other equivalent definitions of matroids. So it's just very hard to get from this statement to that statement. You have to somehow define some combinatorial objects, usually circuits. So circuits are minimal dependent sets. And you have to play with them in a highly non-trivial way. So you don't have to know what's cohomology, or you even don't have to know what's a variety. You just do combinatorics. But still, the proof is challenging. It's like with many combinatorial proofs. It's hard to say why some people can do something and whether others cannot. It's not, I mean, a priori, a 10-year-old child should be able to do it. It's just operation on sets. But having the correct idea to really prove it can take ages. There are references. So if you try it, you fail, and you wonder how people proved it, in the notes there are precise references how to prove it. Okay. Now, people might be a little disappointed that they already thought they know what's a matroid, and I keep on giving you definitions, but trust me, I just give you like a tip of an iceberg of definitions. There are many, many more. And those that I indicate are really crucial. So we have a definition of matroids in terms of independent sets, and we have a definition of matroids in terms of bases. Now, we will define matroids in terms of a rank function. We already know what's a rank of a matroid. It's the cardinality of a basis. Or equivalently, it's a cardinality of a maximal independent set. Yes, because that's a basis. Okay? So let's define a rank function. So we fix a matroid.
Sorry, Mateusz. So if we had the set curly I,
Yes.
we just look at the largest.
Very good. How do we go back? That's the question. If we have basis, how do we reconstruct I? No. Okay, there's a different question. Okay.
No, I just want to say we just have to look at how many elements are there, and the maximal one are.
Or they are bases. They are all of the same cardinality that follows from the axiom, and their cardinality is called the rank. Rank of a matroid. But now we want to define the rank of any subset. So we fix a matroid. And a rank function R, or Rm, if we want to specify the matroids, it associates a number to any subset. So let me tell you that you know rank functions. How do you think? What's the rank of 1, 3? I mean, I haven't yet defined a rank, but if you were to guess. So the rank of the whole matroid is 2. Yeah, this is the cardinality of the largest independent set. What do you think? Guess a number. What's a rank of 1, 3? Guess a number. You can guess a wrong one. Sorry? 1. And okay, so there is a 1 and a 2. And what would you say is a rank of 1, 2?
1.
Okay, so 1, 2, there was only one guess that it gets a 1. For 1, 3, there was a guess that it's either 1 or 2. For 1, 2, 3, we know it's a 2. Okay, and how about if I give you just 3? What do you think would be the rank of one element?
1.
Okay.
I'm thinking about the dimension of the linear set.
Yes, that's a very good intuitive notion. Because the cardinality of a basis is the cardinality of a maximal independent set. And we see that 1, 2 is different from 1, 3. So we would like to have 1, 3 of a bigger rank. So probably a 2. Okay. So at least on this example, you have correctly guessed the ranks of many sets. Now, please tell me what's the definition of a rank of any set. That's what? You have to abstract this notion from linear algebra. So how did we define the rank of a whole matroid? We said it's the largest independent set in that matroid. How will we now define the rank of a subset?
The largest independent set inside the subset.
Very good. That's the definition of a rank. So this is the maximal cardinality of B, where B is inside A and B is an independent set. Yeah? And think about linear algebra. How would you define dimension spanned by a few elements? Well, it's the cardinality of the largest independent set among those elements. Perfect.
So the rank function is unique.
Yes, a rank function is unique and it determines the matroid. If we know the rank function, we know the matroid. How do we go back? If I give you a rank function, how do you give me the matroid back? What's an independent set?
I mean, I would try to find a basis or basis family because.
So how do you define a basis? If I give you a rank function and I give you a set and I ask you, is this a basis?
All sets of the rank function is maximum.
Okay, but notice that if you take the whole set, the rank function will be maximal. And the whole set is rarely a basis, yes? So a rank of 1 to 3 is 2, but 1 to 3 is not a basis. But you are close, let's think.
So you want the rank to be equal to the cardinality of the set?
That's being independent. Well, what does it mean in linear algebra that a set is independent? It means that it spans a vector space of the dimension equal to its cardinality. So that's a small remark. Remark that A is independent even only if the rank of A is the cardinality of A. Yes? So it's always smaller or equal, yes, by definition, because it's the cardinality of a subset. But if it is equal, then we get an independent set. Is this clear? Well, the cardinality of a largest independent set in a set is equal to the cardinality of that set, even only if this set is independent. Okay. So I promised you equivalent definitions for a matroid, and now we know that this rank function determines a matroid. So what will happen now? I have to give you a property when a function is a rank function. So we take now a function. We start from a function, from subsets to integers, and this is a rank function of a matroid if and only if Okay, so what are the properties? What do we know about rank? Try not to look at the notes. What do we know about rank? So what are the easy necessary conditions?
It's not negative.
Very good, it's not negative. We know one more thing, always. What's the rank of an empty set? We take all subsets that are independent, and we take their cardinality. What are the subsets of the empty set? There are not many of them. Yeah?
And that's 0.
Yes, that's 0. Okay, so these are the easy ones. There is one more easy, namely what we have written here. Yeah? So the rank always is less or equal than the cardinality, but we will write it in a slightly different form. What happens when we extend an element by 1? What's the rank of this with respect to the rank of A? Yes, so first of all, it can only grow. That's clear, because here we just take maximum over a bigger family. Yeah? But it cannot grow too much. Plus 1. Okay, so these are easy to guess. There are easy necessary conditions for a rank. And there is one more, which is of course the most interesting. And this one you probably would not guess. It's known as the submodularity. Okay, so it tells us that no matter which sets we take, the rank of the union plus the rank of the intersection of sets is less or equal than the sum of the ranks. It looks maybe a little unintuitive, but if you think about dimensions of vector spaces spanned by them, this is very clear. Because, well, this is the dimension of the space spanned by A union B. Yeah? This is the dimension of the space spanned by A. This is the dimension of the space spanned by B. So what's the difference between this and that? Well, the difference comes from the fact that these subspaces can intersect. Yes? I mean, if they wouldn't intersect, then this would be equal to the sum of those things. But if these spaces intersect, then definitely this set is a subset of this intersection. So this set can span something of dimension not strictly, but at most the dimension of the intersection of these two spaces. Yeah? So this is a translation of the well-known equality that if you have two vector spaces, then the dimension of the union is the sum of dimensions minus the dimension of the intersection. But you have to remember that the intersection of sets does not have to span the intersection of the vector spaces. Yes? For example, you can take two disjoint sets. Yes? Take this will be your one set A, and this will be your second set B. Yeah? Then they don't intersect. Their intersection is empty. But clearly the vector spaces they span, they intersect a lot. Okay. And some people study matroids just looking at submodular functions. That's an equivalent definition. So these are all of the properties we need. It turns out, and you can just look at matroids in terms of submodularity. Okay. Now we come to a very important definition. So the title of the talk is not just Matroids, it's Matroids and Polytopes. So we need to cook up a polytope from a matroid. And this is a very standard construction in combinatorics. Each time you have a family of subsets, you can associate a polytope to it, a lattice polytope. No matter if you have a simplicial complex, if you have whatever, graphs, edges in a graph, and so on. And how do you do this? You look at the set E, and you identify it with a basis of a vector space. So now when I say a basis, I don't mean like a matroid. I just mean a basis as a vector space, okay? So in other words, this is like our, let's say, BE1 plus R B, maybe let's just label them, cardinality of E. Yeah? Okay. And now I want a finite set of points in this vector space, of lattice points. And I have bases, yes? So I have a set of bases. And I want a polytope, a lattice polytope. So how do I cook up points here? Well, I need a lot of them, or at least a few. So I will associate one point to every basis. How do I associate a point to a basis? Forget it's a matroid, forget everything. Just remember that this is a subset of E. What's a natural point in this vector space that will remember this subset?
You can take the sum of all the elements of B.
Yes, this is exactly what we will be doing. We take the sum over all elements of B, and we sum up. Yeah, okay, so now I see I didn't use a very good notation because this basis elements, so let's say that E is just 1 to n, and now we will sum I in B, and this will be just Bi. That's a better notation. Okay? So in our original green matroid, what is the dimension of the space? This space. What will be the dimension? What's the ground set? What's the ground set here? What's the cardinality of the ground set? You can speak just aloud. 3. So we will have a 3-dimensional vector space spanned by 3 vectors corresponding to 1, 2, and 3. How many bases we have? Come on, that's an easy question. How many bases we have? 2. So far we defined 2 points. What are these points in the coordinates? What is this point?
1, 0,
1,
1.
0, 1. And someone else? 0, 1, 1. Okay. So I hope this construction is clear, and now we define a matroid basis polytope.
Sorry, how do you know that? I mean, the B1s or the BIs, do they have to be integer?
BIs are just the basis vectors. So B1 is just 1, 0, 0, 0, 0, 0. B2 is 0, 1, 0, 0, 0, 0, 0.
Okay, but that's not clear. I mean,
this is what I mean by fixing a basis. I choose a basis.
but you can fix any. You can fix also the basis 3 halves 0, 0, 0, 0.
Yes, but I fix a basis corresponding to elements of E.
Okay, still let them correspond to the elements. I mean, do you want integer value bases or not?
So I want bi in coordinates to be 0, 0, 1, 0, 0. If you work in coordinates, you do not have to work in coordinates. This makes sense always. No matter how you made this identification with a basis, but then you have to remember that your lattice is spanned by bi's. But if you want to work in coordinates, that's the easiest way, and then you just identify a subset by putting ones on the corresponding elements.
So can I ask, you could have defined it as like the vector space with elements, with bases, the elements of E, without choosing coordinates.
Yes.
But so you do, and for instance, PB in this case would have been just the sum of,
As written, of bi's.
but
Of the basis elements corresponding to elements of B.
yeah, but just the elements of
Yes,
B.
yes.
So you do in this other way because you want lattice points.
Well, it doesn't really matter. I do this other way because I feel that maybe people are more familiar with 1, 0, 1 than an abstract basis element plus an abstract basis element. Okay. So a definition, a Matroid basis polytope PM is the convex hull of all the points PB over B in beta. Okay? So here it would be just a segment joining these 2 points. Clear? Is the definition clear? Let's take a uniform rank 2 matroid on 4 elements. How many vertices has the associated polytope? So E has 4 elements, and I take a uniform matroid of rank 2. What does it mean? That a subset is independent if it contains at most 2 elements. How many bases are there? 6. So our polytope will have what? How many vertices would it have?
It should have 6.
It should have 6. And you can write them in coordinates, yes? 1, 1, 0, 0, 1, 0, 1, 0, and so on, yes? 2 1s and 2 zeros, and all possibilities. Yes? Is it clear? Very good. So we know Matroid basis polytopes. And now what I want to show you, well, I will not prove it, but you will prove it at home. So a theorem is that for any matroid, the matroid basis polytope is normal. You remember what normal meant? If you scale it, and if you take a lattice point inside the scaling, then if you scaled it by k, this is a sum of k lattice points from the original polytope. Okay? And one of the exercises for you is to prove it for uniform matroids. That's an easy exercise, but we will see a more general proof. Let's make a 7-minute break. This is a non-trivial theorem that for every matroid, the matroid basis polytope is normal. It's due to white. And I will not give you a complete proof. It is in the notes. But I want to present during the lecture the most important tools to solve it. And once you have these tools, you can really do it by yourself. And the first tool is a matroid union theorem. So usually, like domains of mathematics, they have their typical tools. And I would say that Matroid union theorem is a very typical tool to work with matroids. And as the name suggests, it will construct a matroid that is a union of matroids. So we have matroids M1 up to Mk on the same ground set. And let's say that their independent sets are like I1 up to Ik. Okay. How do we define a union of matroids? So what will be an independent set in a union? Well, it will be a union of independent sets. And the theorem tells us that this is in fact a matroid. And further, the theorem also gives us a formula for the rank. Okay, so it's not a completely explicit formula, but it tells us that it's a minimum over all subsets. Here is the cardinality of the difference, and here is the sum of ranks.
But now if you try to identify this with linear subspaces or so, or with vector spaces, then this Matroid union will not really be not really correspond to some vector space.
Not to an easy union of things, because well, its rank is much higher, so it would have to. You cannot work in the same vector space. So it's a non-trivial construction. I should say it's a highly non-trivial construction. And again, you can ask, is there an idea to prove it? And the proof is short and by induction. And there is a precise reference in the notes. But again, I challenge you, try to prove it. Try to prove it. And it's a highly non-trivial combinatorial proof, even if you know that it's easy and goes by induction. It's not, I would say it's much easier than, for example, a multiple symmetric exchange property, but still it's non-obvious. Okay, so let's take it. And what are combinatorists interested in? Well, often if they have a graph, they want to cover it by forests, they want to do such things. So in particular, when they study matroids, they are very much interested when you can cover the whole ground set by independent sets, and how many independent sets do you need to cover the whole ground set. And the following theorem gives us a characterization. So here I hope I don't have to write. Ri is the rank of the matroid Mi. I think it's like clear from the notation. Okay. And the same, when I will write matroid, if I will write R, I will mean the rank function. Okay. Then E can be partitioned into k independent sets even only if for every subset of E we have the following inequality. The cardinality is smaller than k times the rank of A. Is the statement clear? Is it clear what I mean E can be partitioned into K independent sets? Yeah, it means that it's a disjoint union of K independent sets of the matroid M. Okay?
Is that not true? I mean, you can always take one singletons or so, and then...
You can always take singletons, but there is the same K appearing here. So what you are saying is that if you would take K equal to the cardinality of A, this would be trivial. Clearly, E can be partitioned into K independent sets if the singletons are trivial, and the cardinality of A is smaller or equal than the rank of A times the cardinality of E. That's also trivial. But the thing is that you may ask, can I partition my set into two independent sets? It could be a huge set. Can I just take two independent sets, or three, or four? And this theorem tells you that if you want to take 5 independent sets, you have to check this inequality.
So K is the number of how many independent sets?
Yes.
Okay,
Yes.
Dash?
Okay, oh, there should, well, no. There should be no dash. It's not some K independent, it's K independent sets. Okay, so let's prove it. So let's say, first we prove this. So let's say our E is a union of K independent sets. Yeah? So these are the independent sets in E. Yeah? Now we take a set A. What's the rank of A? Where it's clearly bigger than this set. Yes? Because the rank is the cardinality of the largest independent set in A, and this as a subset of an independent set is independent. Yeah? So let's call it A1. It's clearly bigger than rank of A1, and A1 is the intersection of A with the first independent set. First independent set. Okay. Well, it's clearly bigger than the rank of A2. Sorry, not the rank. Well, the rank of A1 is equal to the cardinality of A1 because it's an independent set. Yes? Is it clear? Maybe a question? Some people are nodding, but not everyone. Yeah? Clearly, the rank of A, which is the cardinality of the largest independent set inside A, has to be greater than the cardinality of this. Okay. And we go on until we have the rank of the last set. And this one. Okay? And we sum up these inequalities. What do we get? K times the rank of A is greater or equal than the cardinality of A1 plus the cardinality of AK. What is this? That's the cardinality of A, which is exactly the inequality we wanted. So this implication is obvious. Okay? Now we prove the second implication. Okay, so now we know we have this bound on the cardinality, and we want to show that the ground set can be partitioned into K independent sets. And probably there is a reason why I have written a Matroid union theorem. How will we apply Matroid union theorem to prove this implication? What kind of matroid should we look at? Okay, let me give you a hint. So let's just take M, union M, K times. Yeah? Union in this sense, that I take union of K independent sets. So I apply Matroid union theorem where when M1 is equal to M2 is equal to Mk and is equal to our starting matroid. What are the independent sets here? by definition, what are the independent sets in M union M k times? Just restate the definition. Read the definition from this. Yeah? The independent sets are unions of k independent sets. Yes? What are the independent sets? Unions of k independent sets of M. Yes? So what do we want? Let's call this matroid like M tilde. Well, we want to prove that the whole set is a union of k independent sets of M. Yes? This is what we want. So we want to prove that the whole ground set is an independent set of M tilde. We want that E is independent in M tilde. Yes, this is what we want. We want to present the set as a union of k independent sets. So we want to prove that it is independent in the union of k times the matroid. How to prove using a rank function that the set is independent? What do we want? That this is what? Yes? The cardinality of E. Okay, so this is what we want. Yes? And what does the Matroid union theorem give us? Well, it tells us that it's a certain minimum. It's a minimum over all subsets of E. And then we have to take the cardinality of E minus the cardinality of B. And then we need to add k times the rank of B. Yeah?
I'm sorry. Could we make maybe again clear this this equivalence? So if E is independent, then we know that it's a union of k independent sets, but do those k independent sets have to be disjoint?
Very good question. What if they are not disjoint? So that's a very good question. Why did I jump from a covering to a union of disjoint sets?
So if there is some intersection, you can just throw it away and it's still independent.
Yes. So clearly if I have a union of disjoint sets, that's also a covering. But if you have a covering, and if there is intersection of two sets, remember that the subset of an independent set is also independent. So we can always shrink it. Yeah? So if you have a union of three sets like that, you can say, oh, maybe this set should be smaller. It should be only this. And now you are left with this and the union of those two. Well, these two still intersect, so you can shrink one of them. You can always shrink so that they become disjoint. Very good question. Okay, so what we want to prove is that this minimum is the cardinality of E. Well, clearly this minimum is at most the cardinality of E. Why? Which set B realizes the equality with E? The empty set. Then we get here the cardinality, here we get 0. Yeah? So the only thing we have to prove is that this is not strictly smaller. So we want to show that the cardinality of E minus the cardinality of B plus, did I do it correctly? Okay. No, I did it correctly. Okay. Sorry. So here I just mean a difference. I mean, this is the cardinality of E minus B. Yes? I mean, the theorem would give us the cardinality of E minus B, but this is the cardinality of E minus the cardinality of B. Okay? So we want to prove that this is greater or equal to E. Yes? If we have this, then we already know that this is smaller or equal. So we will have equality, and equality is what we want. Okay? So let's just put it on the correct side. So this means that K times RB is greater or equal than the cardinality of B, which is our assumption. Exactly. And this finishes the proof. Okay? Okay. So armed with Matroid union theorem that helped us to prove the basis covering theorem, you can prove the fact that this polytope is normal. Now we switch gears to Grassmannians. There were no toric varieties so far. Grassmannians. And one of the definitions of the Grassmannians was that this was a GL orbit of the vector E1 wedge EK, GLN orbit, in the projectivization of the kth exterior power of Cn. In other words, you fix a k-dimensional subspace of Cn, and every other k-dimensional subspace can be obtained by changing the coordinates. Okay, this is the Grassmannian, Kn. Now, instead of acting with all invertible matrices, we could ask what happens if we act just with the torus of diagonal matrices. And the questions that motivate us are as follows. We fix a point in the Grassmannian. What does it mean? We fix a subspace spanned by k vectors in an n space. So we can identify P with a class of V1 wedge Vk, which on the other hand can be represented as a matrix, as a k by n matrix, where here we put V1, here we put Vn. Do you remember this? A point in the Grassmannian is a subspace of dimension k, so it is spanned by k vectors of length n. Yes? Okay. Now, if we look at coordinates, so if I write P is the class of V1 wedge Vk, I can try to write it in a basis. E(I1) wedge 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 E(I)k, where I1 is less or equal than Ik. What do I get here? What's the coefficient of the basis? We want to do an example. Yeah? Let's do some example. I take 1, 2, 3, 2, 3, 4. Yeah? So I have a two-dimensional subspace in a three-dimensional subspace. It's a space spanned by these two vectors. And I can write it as E1 plus 2E2 plus 3E3 wedge 2E1 plus 3E2 plus 4E3. And now I can ask, what's the coordinate of E1, E2? What is here? Well, there is E1 wedge E2 with coordinate 3, and there is E2 wedge E1 with coordinate 4. Yeah? So it's 3 minus 4. Do you agree? Do you see it? Okay, so let's ask what's E1 wedge E3. What is this coordinate? Yes? Yes, that's 4 minus 6, which is a minus 2. Very good. Okay, so in general, what's here? How to read it fast from a matrix? Four minus 6. 3 minus 4.
It's a minor.
It's a minor. It's the determinant of, if we call this matrix NP, of, well, we have to take NP, but we have to restrict the columns to I1 up to IK. And formally, we should take a class, because we work in a projective space. Okay. So the coordinates of a point in the Grassmannian are given by all minors of a non-degenerate matrix. Now we can see why this condition is important. It's a non-degenerate matrix because we want the subspace to be k-dimensional. But if it were a degenerate matrix, all of the minors would disappear, and this wouldn't make sense in a projective space. We would just get a 0 point. Very good. So we have this expression. And now we act with a diagonal matrix with T, that is, let's say, lambda 1, lambda n, and zeros here. So what happens if we act with T on P? What happens if we act with T here? Well, this action is linear. So we have to act with T on this vector. How does T act on this? So the first thing I just copy, there is this determinant with I1, IK. And now, how does a diagonal matrix act on basis vectors? Yeah, people are doing this. How does the diagonal matrix ask? Okay, so first, how does it act on EI1? A diagonal matrix on the I first basis vector. How does it act? By?
No.
Lambda I1. Okay, and it rescales all of them. Yeah? So what we get is like lambda I1 times lambda IK, and the same thing. Okay, so I didn't state the questions that guide us, but we want to understand. We want to understand orbit TP and the closure of the orbit. This is some subvariety of a Grassmannian, and we would like to understand it. Okay, so this gives us a parametrization of the orbit. Yes, we can say that the orbit is image. We take lambda 1 up to lambda n in C star to the n. And in coordinates, we have to send it. Well, the coordinates are indexed by increasing sequences from 1 to n. And on a given coordinate, well, we have this determinant of np I1 up to ik, and then we have a product of lambdas. Yeah? So the orbit is the image of this map. Do you agree? I just look at the basis and I write coordinate by coordinate the coefficient. Well, formally, it's a point in the I mean, not a point, but the image is every single, when I fix lambda 1, lambda n, this lives in the projectivization wedge k Cn. Huh? How does the map look like?
So if you forget about the determinant, it would be a monomial.
Perfect. That's a very good observation. If I erased this, I would get a monomial. And why do we love monomial maps? Because they give rise to toric varieties. Okay, so let's think, is it really a problem that I have this determinant? Is it really a problem? Well, it seems it's not a big problem because I can define a linear automorphism of the projective spaces. Yeah? A linear automorphism that just scales a basis vector. A linear diagonal automorphism. Yeah? A map that just sends EI1 wedge EIK to 1 over the determinant NP I1 IK. EI1 wedge EIK. Yeah? It just scales.
So, but NP depends on P. I mean,
Yeah, so we fix a P, we fix one P, and we ask for the orbit of that P. So when we vary P, we get a different automorphism and we get a different image. That's true. But if we fix a P, the orbit, so what I write now will be not true, but let me still write it, is an image of lambda 1, lambda n, lambda I1, lambda IK, I1 less than IK. Sorry, it's not an image, it's isomorphic. Isomorphic. 2. Yeah, it seems I just do an automorphism like that and I get this map. It seems correct. So let's do an example. I will take a point P in the Grassmannian G24, and our aim will be to understand the orbit and the closure of the orbit of this point. And I take a specific point. I take a point that corresponds to this matrix, 1, 0, 0, 0, 1, 2, 3, 4. So this is a matrix that represents a point in the Grassmannian G24. Is it clear what kind of subspace I mean? It's a 2-dimensional subspace spanned by these two vectors in a 4-dimensional space. Okay? Okay, so what's V1 wedge V2? What do we have? What is the coordinate of E1 wedge E2? 2. What is the coordinate of E1 wedge E3? Someone else, come on. 3. Now someone even else. What's the coordinate of E1 wedge E4? 4. Okay. What is the coordinate of E2 wedge E3? 0. Okay, so all the other coordinates will be 0, can you see? So, and maybe you notice a problem. The 0, okay, now I act with t, and here I get lambda 1, lambda 2, here I get lambda 1, lambda 3, here I get lambda 1, lambda 4, here I get lambda 2, lambda 3, but it's times 0. And I cannot rescale 1 over the determinant. So this statement would tell us that the orbit is the image of like lambda 1, lambda 2, lambda 1, lambda 3, lambda 1, lambda 4, lambda 2, lambda 3, and so on. But this doesn't appear at all. So what is really the orbit? The orbit is the image, or it's isomorphic, Well, this I have to take, this I have to take, this I have to take, but the other things are 0. So I don't even have to take them. Okay? Do you agree? We have written what's the point in the orbit for arbitrary t, and when we vary t, these things change, but these things don't because they are multiplied by 0. Okay, so now do you remember, oh sorry, that's, yeah, lambda 1, lambda 3, lambda 4. Yeah, we have 4. We have a 4-dimensional torus. Okay. What is the associated toric variety and what is the polytope? So first let's start, what is the polytope of this map? How many points will this polytope have?
What is the polytope of a map?
Well, so there was a lecture about toric varieties, and if we have a monomial map, what did we take as points of the polytope? The exponents. You remember? Monomial maps were encoded by exponents. So what's the exponent here?
1, 1, 0.
1, 1, 0, 0, because there is no lambda 3, lambda 4. What's here?
1, 0, 1, 0.
1, 0, 1, 0. And here? 1, 0, 0, 1. What is this polytope? That's very good, but it has a simpler name than a simplex.
Triangle.
It's a triangle. So what's the toric variety? What's the dimension of this triangle? As any other triangle, it has dimension 2. Yeah, so what is the toric variety associated to a 2-dimensional triangle?
Isn't that the plane?
Yes, it's a P2. So the closure of the orbit is just a P2. And we see it from toric geometry, because the polytope is just a triangle. It's a 2-dimensional simplex. Okay. Where are the matroids? Where are they hiding here? Okay, so let's make this statement correct. So an orbit is isomorphic to an image of a map, but here we cannot take all sequences. Which sequences do we have to take? Such that what? Such that what? Yeah, so here we had to forget, for example, lambda 2, lambda 3. Why did we have to forget it? Because it was 0 here. It was multiplied by 0. What was the 0? It was a minor. The minor was 0. So we have to assure that what? That this minor is non-zero. Okay. Do we have this matrix? I erased it. So remember, we have this K by N matrix. Yeah? K by N matrix. I promised you that matroids are like matrices. How to cook up a matroid from a matrix? A representable matroid. Can you find a finite subset of some vector space?
You could just say the columns.
Columns, very good. So let's look at this matroid. Let M be a matroid of columns of NP. Okay, what's the cardinality of a ground set? Just to check if we are talking about the same matroid. It's n, because there are n columns. So every column gives us a point. What's the rank of this matroid?
K.
Okay, why k?
There are all minors or non-zero.
Not all minors, but there exists a non-zero minor because this is a full rank matrix. because the rows span a k-dimensional space. And if the rows span a k-dimensional space, the columns also span a k-dimensional space. Yeah, we know this from linear algebra. Okay. What are the bases of this matroid? When I1 up to ik, so the rank is k, so it has to be a k-element subset, is a basis. Even only if what happens? Yes, if the columns are independent, if columns I1, ik are independent, and this is even only if what? The minor is non-zero. Okay, so there is some relation to this map. Okay, so if you understand, the map takes those monomials such that the minor is non-zero. And for this matroid, the minor is non-zero even only if this is a basis. So the closure of the orbit is a toric variety because it is a closure of a monomial map with the polytope that is what? Let's do this example. What are the bases of this matroid here? What is the base set here?
All sets of cardinality 2, which contain columns.
Very good. 1, 2, 1, 3, 1, 4. Yeah? This is the base set. What's the matroid base polytope? How many vertices will it have?
3.
What will be the vertices?
Yeah. 1, 1, 0, and so on.
Yeah? What was the polytope representing the map?
The same.
Is it a coincidence? No, we just proved it. Because here we take things that where the minor doesn't vanish, and the minor doesn't vanish exactly when this is a basis, and the matroid basis polytopes just takes the basis. And then when you take a toric variety associated to a polytope, you just take the products of the things that were the vertices. So how to finish this sentence? The closure of an orbit is a toric variety with the polytope that is? The basis polytope of the associated matroid. Okay, note that we did something non-trivial here, because this matrix NP is defined in terms of columns, and in terms of rows. We take the vectors that span a k-dimensional subspace in an n-dimensional space. And the matroid is defined by the columns of that matrix. And yet, the toric variety associated to the Grassmannian, the orbit in the Grassmannian, is the toric variety associated to the matroid. It is the matroid basis polytope. And this is, well, the proof, when you look at it, it sounds trivial. I mean, I basically wasn't proving anything. I was just restating. But this was a very nice result by Gelfand, Zelewinsky, Serganova, McPherson. Sorry, Gelfand, Gorski, Serganova, McPherson. And they were very happy when they observed. When you read their article, you can see that, oh, it's amazing that people haven't realized this so far. It's a really nice relation. So I wanted to point out that this tells us something about the geometry of the torus orbits in the Grassmannians. In the first half of the lecture, we have proved that the polytopes are normal. And if you remember the toric lecture, I told you that the normality is a statement about singularities of the variety. And in fact, what we have proved is a highly non-trivial fact, that the closure of any torus orbit of any point in a Grassmannian is projectively normal. And I believe that without matroids and toric geometry, it would be extremely hard to prove it. And now we have this statement. And in the last 10 minutes, I wanted to go back to algebraic geometry. So what is algebraic geometry about? Well, old-fashioned people say that it's about polynomial equations and their geometry. And we have not seen here polynomial equations. I mean, I've been talking about geometry, but there were no polynomials. Okay? So let's try to say, what are the equations? What are the equations? What is the ideal of this torus orbit closure? And this fact that this is a toric variety tells us that this is generated by binomials. Okay, and if you remember the toric lecture, then you remember that the equations, which is something hard, is really encoded by integral relations among basis elements. Yes? Okay. So we have the Matroid basis polytope. Yeah? And it is the convex hull of points of this form, 1, 0, 1, 1, 0, where and so on, where these are elements of the basis. Yeah, so this is the point PB. Yes, you remember. Okay, what does it mean that PB1 plus PB2 plus PBK is equal to PB1 prime plus PBK prime? What does this mean? So PB1 is a point that has zeros everywhere, and it has only ones for elements of B1. The same for B2. And when this equality holds, what does this mean?
Definitely holds if you have a permutation of the...
It definitely holds when it has a permutation, but this is something not interesting because we will translate it to a binomial xb1 times xbk minus xb1 prime times xbk prime. So if this is a permutation, this binomial would be 0. But let's try to look at it in terms of combinatorics of a matroid. What does it tell us about the union of bi's as the multiset? So notice that adding these points is basically taking a union as a multiset. Yeah? If I have a set with these two elements and with these two elements, so let's not label them 1, 2, 3. So if I have 1, 1, 0 plus 0, 1, 1, this is 1, 2, 1, which would also be the union as a multiset.
What do you mean union as a multiset?
I just mean that this can contain an element a few times. So a union of 1, 2 as a multiset with 2, 3 is not 1, 2, 3. It's 1, 2, 2, 3. Yeah? And now it's clear that adding these points is the same. So this is equivalent that this as a multiset is equal to this as a multiset. Yeah, I'm just translating the fact that adding coordinates is the same thing as taking a multiset. So what we have proved so far is that the equations of the torus orbit closure, they correspond to such relations in a matroid that the union of certain bases is a union of some other bases as a multiset. And now I want to tell you that you already know a lot of quadratic relations for a matroid. Let us take two bases, because we will be looking for a quadratic relation. I take two bases of a matroid, B1, B2. How can I build such a relation that B1 union B2 is a union of two other bases? How do I do this?
Is the property like I remove an element from one and I add the other?
Exactly. So the axiom of a matroid, well, not the axiom, but one of those properties was that if I take a B1 in B, then there exists a B2 such that I have two other bases. Let's say minus B2, such that B1 union B2, I already forget the brackets, is in a basis, and B2 minus B2 union B1 is in a basis. You remember? There was a symmetric basis exchange. So let's call this B1 prime. Let's call this B2 prime. Yeah? And clearly B1 union B2 is B1 prime union B2 prime. Yeah? So what did we prove? Symmetric basis exchanges give us quadrics, binomial quadrics in the ideal of toric variety associated to the basis polytope. Okay, and I have 1 more minute, and I wanted to end those lectures. This is the last lecture with some open problems, so that you don't only have to solve exercise, you can actually solve an open problem. So this is a conjecture due to white. And there are two versions of it. So the first one is that symmetric basis exchanges give generators of the ideal. So far we only produced some elements, and the conjecture is that these are enough to generate. And if you think that this one is too hard, you can prove a weaker one, namely that this ideal is generated by quadrics. So we even don't know if they are equivalent. So we even don't know if these quadrics, if their linear combinations give all quadrics. But these are two conjectures. And if even this seems too hard, you can prove it in a representable case. So what you have to prove is that the ideal of any torus orbit in any Grassmannian is generated by quadrics, or the quadrics associated to the symmetric basis exchanges if you want a more challenging problem. Thank you very much.